Okay, I think I can start. So my screen is visible, right? At least
Yes.
someone just yes,
Yes,
okay.
yes, yes.
And
Yeah.
guys, it's a request actually. So start. Please join by like 3 o'clock. Otherwise, every time I have to just keep on accepting the people whoever is joining. So it's actually a bit distracting. I mean, if you are joining for the class, better you all join by like at most 3 or 5. After that, I don't have to like press every time admit someone. So then it will be better for everyone. See, still people are joining. Yeah, so from next class, please make sure that you join in proper right time. Yeah. So the way, okay, again someone is joining. Okay, the way I have planned actually. So as technically this is the first session because the last week there was some technical issue, so I couldn't really teach. So I was just thinking, I'll first part means the first it's a 2 hour class. So first hour basically I will try to like start with some basic concepts of the semiconductor physics as a introduction, and then I will just go through some of the couple of sample question and answer, so that will be also helpful, I think. So mostly people are from graduation background, right? Can someone tell? Like,
Yeah.
okay, fine, good. So yeah, myself is Pritam. Just a brief introduction. I'm a PhD student from Indian Institute of Science. So I'll be taking the TA course from now on. I hope most of the people have already joined. So it's better we can just start. So as you guys all know, like in most of the modern electronic devices, basically it's made of semiconductors. So generally for insulators, it don't like conduct current, but metal is actually considered as a very good conductor of electricity. But semiconductor are basically a material whose conductivity is basically lies between those of an insulator and a conductor. So the property is somewhat intermediate. That is why it is called semiconductor, right? So silicon and germanium are basically the available most standard semiconductor we can think of, which are mostly crystalline solid, and they have a diamond lattice structure. And yeah, so first I'll the screen. I hope the screen is visible. And if any point of time, if someone is feeling that the screen is getting frozen or it's stuck, please inform me. Yeah. Okay. Generally, if I just consider a atom, so this is something of a silicon crystal. And think of these are the electrons configuration. Valency is 4.
बोल सुके
Guys, please mute yourself.
ना આ ક્યાં લખવાનો સ્ક્રીનશોટ લઈ લે
We can't hear you.
Pritam, we're not able to hear you.
We're not able to hear you. I think you're on mute.
Hello.
Yeah,
Yeah, now
now
we
we
can
are
hear.
able to hear. Yeah.
Yeah, yeah. Okay, fine, fine. Sorry. Actually, I think maybe I have unmuted. So now I think it's fine, right? So
Yes.
probably I'll just quickly repeat. I was just giving some basic introduction about the semiconductor. Like you guys already
Sir.
familiar. I think the
Sir.
semiconductor is. Tell me. Go on.
You will provide this PPT presentation.
Yeah, I will provide that. But the first class, I just thought ki it will be a kind of introductory session, and I will discuss some of the problem and answer. Is that okay? Then from the second class, I can do that.
Okay, sir.
Okay, so can someone just tell me? You can also tell ki what are the things you have seen in the class, what sir had already taken, so that I can also. What are the topic basically were discussed in the last class?
Last class.
Like what Digvijay sir was taking, right? You guys from NPTL, right? Some of our from different college also, I know.
Last class was not taken. Some technical issues.
No, no, that is the from my side. No, that is a TSF session. But you guys are also attending the classes, right? This is the your. Yeah. So did you attend those classes on NPTL or not?
Yes, yes.
Oh, that's what I'm asking. Ki what are the things were taught like in the first? Maybe it was the second class that happened, right? So far on the NPTL side.
Total, yeah, 2 weeks of classes are over now.
Yeah,
So,
yeah, that's what I'm
yeah.
saying. Ki what are the topics were covered? Just if you just quickly highlight, if possible.
In the week
Hello,
first, it's
sir.
just introduction of semiconductors, then energy bands, then the
Okay.
fundamentals of all energy bands, and after doping and what is intrinsic and
Yeah,
intrinsic
yeah, all those
semiconductors.
things,
And when
band
we,
theory and all.
yeah,
Okay, okay,
yes, yes, yeah,
fine,
and the
fine.
temperature
So I can
dependent.
actually, as it is a first class technically, so I just thought I'll give you a brief introduction. Then I can quickly move through some of the problems, important problems like that will be also useful for some competitive exam like JAM and JIS, right? So I think that is fine. Yeah, there are some other students also from different college. Maybe they also joined. So I think yeah, I'll try to give a first class bit simple. Then probably from the second class, I will give a proper PPT also, or mostly I'll be using the iPad because so that I will give you the questions, some sample question that I have prepared, and I can solve online only. Okay.
Okay, yeah.
Yeah. So basically, there are two types of semiconductor. I think just a quick recap. It's a N-type semiconductor, and there is a P-type semiconductor. Yeah, suppose impurity like arsenic and antimony or phosphorus is added with a very small percentage to let's say either silicon or germanium. Then probably this impurity displays some of the silicon atom in this lattice. What I was telling you. So just 1 second, I'll admit someone. Yeah. So those are called in that case. The energy is required slightly. It will detach this fifth electron from the impurity state. So and which has an order of let's say 0.05 electron volt, and for this for silicon, and for germanium it's 0.01. This is called the ionization energy. So how much energy is basically required to switch one electron from the atoms, and that is called the ionization energy. Okay, so next is I'll draw this thing. The energy band structure. In solid. Yeah, let's say I have a conduction band. This is how we basically all the time define, and you will also see ki some of the problem for mentioning what is the band gap for a material. And
Hello, join.
okay, yeah,
Sure, Nikanchal.
this is your conduction band. So along y-axis, let's say I'm plotting the energy. So I'll give a 3 examples so that you can just understand the basics. And this is your valence band. So there is a certain gap, right? You can see there is no density of states are there. I mean, electron or holes, whatever you can think, they cannot stay in this intermediate region. So this is something energetically forbidden. One second, let me change the color. Yeah. So this region you can consider it as a forbidden region. So they, in terms of condensed matter physics, you can say, okay, there is no density of states. That's why electron cannot occupy any of the state. It has to jump from this valence band to the conduction band. So let's say I'm exciting the my system with some photons or with several electron volts, then it can occupy a state in the conduction band accordingly. Okay. So this is something when the my band gap is very high. I mean, it's not something it's close to semiconductor. Then let's say of the order of 3 or 4 electron volt. Then we can consider this as a insulator. Okay. And next, let's say I have the band gap is very small, not like 5-6 electron volt or so. It's very close by to each other. All this conduction band and valence band. This is valence band. This is conduction band. So you can consider this relatively close to 1 electron volt or so. Then we consider this system as called semiconductor, right? And the other one in the solid, basically what you all know, it's metal or perfect conductor. Okay. Here what happens, okay, your conduction band and the valence band almost overlap to each other, right? So you do not have a need to put any other extra energy to make the transition. Even at electrons are already occupying some of the portion of the conduction band. Okay. So these are widely regarded or known as conductor, or you can also consider as a metal. Okay. So semiconductor is something which is lying at the middle of these two, insulator and the metal. So this is the overlap region. Okay, typically, so if I be more quantitative, this band gap, this forbidden area region, so is this value, always you guys try to remember, these are very important piece of information. For let's say for silicon, the value of this forbidden band gap is 1.12 electron volt, and whereas for germanium it's close to 0.72 electron volt. Okay. So this is again at room temperature. So these things are actually temperature dependent quantity. So that I will come later. How this you can tune the band gap of different materials, like with respect to different temperatures.
I have a
So
question.
there
You
is,
said,
yeah,
yeah, between valence band and conduction band, that is a forbidden region
yeah,
where we cannot find any free electrons. Is it
yeah.
only the ideal one, or even with the practical one also, there it is not? It is a forbidden
So
one.
if you can create an intermediate state, this is something called defect state. Okay. So it is the ideal condition. So if you can create a, so you can see my screen, right? So you can, I will
Yes.
put a different color. Okay, one sec. So let's say you can creating a local defect state to this all ideal semiconductor. Okay. Then what happened? There is a chance that you can see there's a certain region here. The density of states is not zero now. This is something I'm talking about realistically. If you introduce some defect, then electron can make the transition in the intermediate zone. Okay. But in the ideal case, let's say it's of the order of 1 electron volt only. Understood? This is something is called defect state.
Okay, okay. Only for intrinsic, you mean to say it is forbidden.
Yes, right.
Okay,
Got it.
got it.
Yeah.
Thank you.
Okay. So there are two different kinds of semiconductor again. So let's say we can also categorize something called direct and indirect semiconductor. These are very important in terms of like application. Direct band gap semiconductor and indirect band gap semiconductor. So the examples are gallium arsenide and indium phosphide. So here what happens if I try to draw the energy band diagram. So let's say this is my conduction band and this is my valence band. So this is in the your in E versus K space, right? So if you have a real lattice and then if you do, sorry. Yeah. So that is why it is called E versus K. So this is my wave vector and along Y direction, you can think of your energy. Okay. So here what happens when I am basically the electrons and holes are making the transition, you can see the K point literally that is on the X axis, right? If it is making the transition, so my wave, the momentum, so which is momentum is again, you can consider it's H cut K, right? So my momentum is conserved in this case. If it is a direct band gap semiconductor. For direct band gap semiconductor, so it can only change the energy from this to this point. Okay, so without even changing the wave vector. So this is just the direct recombination of your electrons and holes. So in today's class, I'm still admitting whoever is joining. I can see still there are a lot of people in waiting in lobby. I admitted all of them. But from the next class, I won't admit anyone who is basically joining after 3:05 because it can basically disturb the other student also, right? I have to stop and admit the other people. So it's a request you join at least by 3:05 at most. Okay, so in this case, there is a direct, I was saying there is a direct recombination of the electron and holes. Because once the electron, once the electron leaves this place, so there will be automatically a vacancy in this place, right? So somewhat like because of the charge conservation, the hole should be there. So that is something called electron hole recombination. So that is why there's a problem in the iPad. Yeah. And the excess energy here, basically, what is happening will emit in forms of the photon, which you can consider is h nu, where h is the Planck constant and nu is the your frequency of that particular emitted photon. Okay. So this is an important one. Sometimes generally you will be expect ki your forbidden energy gap will be provided and you will be asked ki what are the frequency of this emitted photon. So the minimum frequency of the emitted photon in this during this process of generation and recombination process. So let's say this gap is of the order of Eg. So that is my forbidden gap in terms of electron volt. Okay. So you have to basically convert it to the joule then to find out in terms of Hertz. So this is the emitted photon energy, which will be given by Eg equals to h nu, and you can find that it will be just simply this. So this kind of semiconductor is direct band gap semiconductor. It's mostly suitable for application in laser and LEDs. Okay. So there are indirect band gap semiconductor, the or itself the germanium and the silicon. I'll tell that why it is called so. Indirect band gap semiconductor. This is silicon and germanium. Okay. So here what happens? Your the conduction band. This is very important concept actually. The conduction band and the valence band. Let's say I'm drawing this line in my energy space. This is my k wave vector. Let me change the color. Okay. This is my k wave vector along x direction, and this is my energy along y direction. Okay. So now you can see this valence band and conduction band are no longer aligned for a same k value, right? So in order to make a transition for any kind of electron from valence band to the conduction band, it cannot like go directly. So if you see, so it will go, but the problem is it has to change. Let's say I'm starting from k equals to 0, but it cannot make the transition to k equals to 0 because there is nothing. So it has to do the transition to k equals to k1. So you can see there is a change in momentum, which is defined by h cut delta k, which is k1 minus k equals to 0. So here momentum is not conserved. Okay. So there is no direct recombination of the electron and holes in this process. So here basically you need a traps or like some kind of recombination center which will contribute to the defect state in the band gap. Okay. Such like a location which generally acts as a third body which helps to satisfy the requirement of the momentum conservation. So in order to conserve the momentum, we need a third body which generally considered as any kind of defect state. Okay. So as a result, energy is liberated, generally goes to the heat into the crystal. So this type of semiconductor is generally used for like construction of the diodes and the transistor, something like that. And they are not basically suitable for optoelectronic device. So these are not suitable for, so the indirect band gap semiconductors like germanium and silicon is not suitable for any kind of optoelectronic transport or other optoelectronic devices. So now this part is complete. I'll come to the carrier concentration. You can write it as a heading of this section. So carrier concentration. If you have any doubt so far, you can ask me.
Hello, sir.
Yeah, go on.
Sir, what do you mean by density of states? Can you express it for 1 dimension, 2 dimension, 3 dimension?
Oh, it's basically how many states are, one second, how many states are there in the wave vectors space, like something like dE, dk. So this is how we define, like if we integrate, so how many states we are getting from k1 to k2. So you have a lot of states in your, let's say, Fourier space, right? Which is your wave vector. So this is how we generally defines. So where there are electrons, because electrons can only occupy like because of the Pauli exclusion principle, so one state can only occupy one electron, right? You can also think of two, because this can have spin spin half, and this can have like spin minus half. So you can at most consider key, okay, at a particular state you can have this two electron. So this is a plus half electron, and this is a and this is minus half. So this is how you basically define all how many states are there in a particular wave vector space, right? This is how we define the density of space. It's basically density in your Fermi space, because you have a real lattice. If you do the Fourier transform, you will be leaded to the x inverse, which is k. This is called the wave vector. Yeah. Is this clear?
Yes, sir.
Okay. And here you can see, as I just mentioned, there is no states are available, right? It has a certain density, certain states, and certain density in your energy space. So that is how the electronic transport occur in any kind of solid. It has to occupy some of the state, right? So those are called the electronic state in a band, and it has a certain density which is defined by, like, of course, I mean, there will be some band you will find it's a parabolic, right? It has k square. So you can easily find what will be the density just by doing daily del k. That's it. Yeah. Yeah. So in order to just calculate the conductivity, because ultimately if you do any kind of electrical transport, you have to measure a quantity, right? So that is called the conductivity, which is also defined as a sigma. Okay. So it basically we can tell about the density of the electrons in the conduction band and the density of holes in the valence band. So generally there are certain assumption. We assume that the temperature and the carrier densities are to be small, so that the electron gas in the conduction band and the whole gas in the valence state are non-degenerate. Okay. So the now I'll come to the particularly the density of states part, which were you were mentioning that time. It will be useful for this now. It varies from system to system. Let's say I'm talking about first this. Okay, I'm talking about the, let's say first start with the conduction band. Okay, so conduction band, I'm just writing CV in short, which is given by the standard expression. This from the Fermi Dirac equation, you can get all this information. These are not very difficult to derive, but it will take time, so I'm not deriving. Okay, so this is C is basically your constant, where rather change the color. So this is the density of states of the free electron gas in the conduction band. Okay. So here basically your ME star, this is something is called effective mass, because we have a certain periodic potential, because electrons are no longer completely, I mean, if we're talking about a solid, then your effective mass will slightly change. Like generally it's 9.11 times 10 power minus 31 kg for electron, but under some potential it will take a form of effective mass, so that we don't have to incorporate the force term, but rather than we are modifying the mass of the electron. Okay, this is a simplistic way we can say. Okay, under any, if we have to write some kind of density of stress expression, this is how we write. And basically your EC is the energy which corresponds to the bottom of the conduction band. Okay, like this is my let's say this is my conduction band, okay, and this is my valence band. So let me define this thing as EC. Okay, so this is the basically bottom. So again, if I make it more elaborative, so this is your energy. This is your energy. Let's say starting from this point. Okay,
Hello,
and
sir.
this hit is hitting. Yeah.
Sir, ME star means effective.
Mass. Sorry, this is mass. Yeah, I'll clearly write.
Effective mass of electron, right?
Yes. Effective mass of electron. Yes.
Yeah. So why
Effective.
we use effective mass instead of mass in case of semiconductors?
You when you are confining an electron in a system, it cannot take the simple rest mass, right?
Yeah.
It is under some potential. So basically, you have to modify in a solid. Basically, you have to modify with the effective mass. So basically, without going into the complexity of the dynamics of the electron, I mean, we are not even incorporating all this force and all these other dynamics. Rather than we are modifying the mass of the electron. So let's say when you are in a lift or like some other planet, so your mass will be not like what we consider for the rest frame or the under the like when you are in the earth. So generally the mass always depends on what situation you are in, right? What is the surroundings of it, how you are interacting with the with that medium, and all this interacting and gravitational effect will determine the effective mass at that time. So you can consider in that way ki, okay, you can also write ki my acceleration is this, but rather than I'm keeping the acceleration same and putting the okay the g the standard 9.8 something. So where instead of changing your this thing, so which involves the force and all this term, you rather than modifying your mass. This is a simple way I can tell you. So it's better to deal with that rather than going into the complexity of the classical picture dynamics, like what are the force is getting applied and all these things. So in solid, this is a very simple thing to consider because these are also confined in under some potential, right?
Okay, sir.
Because after all, it's a band. Yeah, it's not a single electron anymore, right? It's not a free electron that you are putting a Coulomb potential. Okay, well, let me tell you. So there will be two electrons, and what are the forces? There are numerous numbers of electron that is present in a solid band. So that is how mass is no longer its same knot. We have to modify it in order to incorporate all other interaction. Yeah, this is how it has been defined. I mean, there is no as such ki, okay, we have to go this way, but this is the simplest way that you can yeah adopt to solve the problem. Okay, fine. So I hope you got your answer. And the now I'll write, this is something you already familiar, that the probability that a state basically which corresponds to like with the energy E is occupied is the probability is given by Fermi-Dirac distribution. So this though I think you guys are familiar. I don't know, like there will be some student of different years of graduation maybe, but you can just because these are the important thing for the course, so you guys can note it down. So this is something called the Fermi-Dirac distribution, and electrons are all fermions. So electron has to obey this Fermi-Dirac statistics in order to make any kind of like how it is basically populating in a particular state, and what is the Fermi energy at and what is the temperature. So all this information are already loaded in this equations, and based on that, electron has to obey this equation in order to occupy a state. Okay, this is very standard, and EF is called the Fermi energy of the electron. Now, therefore, let's say the number of electrons, let's say how many electrons are there. Let's say the number of electrons which are lying in the energy range E. I'm using some shortcut notation. Okay, I'm not going to write all the sentence. That is why I'm keep on telling. So let's say in the energy range of E and E plus delta E, and this is the energy range because we are going to define the density of states, right? In the spatial, like in the volume as well as in the energy. Okay. Now it has to come when we talk about the density also, it has to be divided with the volume, right? Or you can write per unit volume in the conduction band. Okay. It is equal to, again you have to put the Fermi-Dirac distribution because you know electron cannot occupy, like two electrons cannot occupy the single same state, right? So I'm not incorporating all this degeneracy right now, but in a simple picture you can write down this. Okay, this is my density of the electrons, and if we just integrate it, let's say from particularly in the conduction band, so dn is basically a small portion in the, let's say if I change the color, so dn is just a small portion. Okay, now my conduction band is not like limited in that region. You have to integrate starting from what I just shown you. If we consider, so here is the band gap, okay, which is already we have defined as, I think Eg maybe, yeah. So starting from here all the way up to infinity. Okay, so you have to integrate to find out the density. So this is a very important formula actually. I mean, you will sometimes you guys will be provided with the density of states. Okay, then find out what will be the density of states of the electron in that particular band. So this is something. This is a concept which could be important for other examples also. So generally, the upper limit is taken to infinity instead of the top of the conduction band. Okay, so this is the allowed because the distribution function will be applicable only around the EC and practically zero for E greater than EC. Okay, so technically this even if you put infinity, okay, if it is goes beyond E greater than EC, then simply if you will drop down to zero. Okay, so technically it doesn't matter, like that is why we are taking infinity for the simple solution. Okay, now at low temperature, and for E greater than equals to EC, okay, so already we are in the, okay, still someone is joining. Already it's been 45 minutes of the class. Okay, fine. I don't know what you guys will understand from this. Already I'm middle of the class, but anyway, you guys can note it down. So yeah, so now this equation particularly, if I plug this in, the Fermi-Dirac distribution will this already, which we know, and then which corresponds me to this n. C I'm not like writing now, so just do the integration. Then my Fermi-Dirac distribution. Okay. Now let's we have to solve this, right? So now for the sake of simplicity, let's consider this E minus EC by KT, because it will have a thermal broadening because temperature is not zero. We're talking about the finite thermal effect in the system. So electron also gains some energy from the temperature. So consider this thing as x. So let's see how we can modify my n now. So this is EC minus EF. Yeah. Okay. Then KT 3/2. Okay, this is x, right? E to the power minus x dx. Okay, it's become much simpler now. If we do this substitution in this integral, I'm not elaborately doing all these things because these are not that important, but yeah, in the already know all this value. So if you do the integration, you will get this value root pi by 2. Okay, then you plug it in the final results. This constant term we can write as NC. There is a rationale behind why we are doing this. So this expression will be very important for your next set of in the due course. Basically, we'll keep on taking this thing. So this is basically a you can see this NC has a dimension of the concentration. Okay, that is why we are defining like it's in the conduction band. So dimension of the concentration. Now
Sir.
again we'll do this. Yeah. Any questions?
Yes, sir. What is the physical significance of Fermi level?
Yeah, it's basically for to what extent the electron can occupy in the energy space. So that is basically you can consider or think of a Fermi sphere. Okay, so the basically above the Fermi sphere, your this Fe, whatever Fermi Dirac distribution I have told you, will be zero. Okay, electron can populate till that sphere. So that's where my conduction is confined. Okay, that is the concept of the Fermi sphere, and that is how we are. Maybe it's a 2D or 1D. Based on that, we can think about all these Fermi energy levels. Okay.
And Fermi integral of half order.
Sorry.
Fermi integral of half order.
Fermi integral of half order. Okay, so
Yeah.
let me just show you something. I don't know what do you mean by Fermi integral of half order, but okay, let's say this is my Fermi energy. So are you familiar with this plot? So this is at absolute temperature, T equals to 0. Okay. So either electron, if you see, can you see what I'm writing? Hello.
Yes.
Yes.
Yes. Good. Okay, fine. So this is your Fermi Dirac distribution function. So now I'm talking about, let's say, the very like crude way. So I'm at a 0 Kelvin temperature. Okay. So this is from the Fermi Dirac distribution. So all the electrons are occupying the states, which is you can still put a equality symbol, but mostly it is defined in this way. It is 1 for whoever the electrons are occupying within the Fermi sphere, and this Fermi energy, this is the limit basically. Okay, 0 to EF. You can think of 1 dimension, 2 dimension, 3 dimension, whatever, but this is the your like basics. Okay, this is the like if you do that some kind of okay, this is the your basically the sphere. So within that electron will populate. Beyond this, the energy of the electrons of this outside the Fermi sphere, electron cannot occupy. So it's basically the probability, right? I already told you that whether the electron, what is the probability of occupying a state with energy E. So the probability goes down to 0. But this is not the case. If you slightly increase the temperature, then you will find the step-like kind of function. It will have a thermal broadening slightly outside this thing because of the finite thermal energy. Electron can slightly push beyond this limit. So it will automatically get, this formula will get modified with that. So yeah, I hope you understood this thing, or this Fermi
Yes, sir.
energy, and
Ye-
yeah, so
yes, sir.
yeah, fine. Yeah, so I was doing this thing, right? Yeah, got it, fine. So this is the, you can the density in the conduction band. Let me conclude this part first. So I'll change the color. Okay, so yeah. So this expression is very important actually. I mean, these are very commonly used expression. We will also expect some question in jam and just based on this formula. So you can write it down, all this thing, and try to remember all this at any time. Yeah. Now, if we do the same thing at the whole side, okay. So this is for the conduction band, right? So now, if we talk about the valence band, basically the whole dope side. What will be the G? Can anyone tell me? If I put the same C, let's say, like this is my, so let's say this is, I'm defining as EV, the upper one. The way I have defined it, like EC. Can someone tell me? Simple, no?
How many states are available?
So that is irrelevant right now, right? So if I'm starting with the density of states, so the way I started right now, like few minutes back, this one, right? I've already given you the information. Okay, the age of the valence band is EV, and C is already, it's already solved. So basically, you have to replace the EC with EV, but the maximum energy of the valence band is now not EC, it's EV. So your E is always less than EV, right? In those case, for the conduction band, E was always greater than EC. That's the thing is different. So basically, you have to subtract from EB, not from E. That's the difference. Okay. Because in between EC and EV, there is no state, right? That portion is already forbidden. Okay. Now we'll try to solve this. C is as it is. Like you can consider all this information of the effective mass of the hole, maybe or may not, we don't know whether it's equal or not. Okay, I'm not taking anything about this. It hold or may not hold the effective mass. It's better you write as m whole star for the effective mass. Got it? So now the thing is, since the hole signifies the unoccupied state, right? Because electron already made the transition, so the Fermi function for the hole, this is something you have to understand, or the Fermi function for the hole is basically now 1 minus Fe. Okay, so my total sum of Fe is always 1 for electron and hole. So for the electron, once I have this information, okay, my distribution or probability distribution function is Fe. So for hole, it will be simply 1 minus Fe, right? So which basically represents the probability, the total, this one, 1 minus Fe, not only Fe, is represents Just 1 minute. I'll connect to the charger because my iPad is almost about to die. The battery is very low. Guys, can you see my screen?
Yes.
Okay, fine. So actually the battery was very down, so I had to reconnect. Sorry. Yeah, I'll just go back to this. So this 1 minus Fe basically represents probability of not occupying the energy state E by an electron. Okay, so that is not possible. It's basically you will violate the energy conservation rule. So now at low temperature, basically why we're considering this, there is no thermal prodding, because I just told you, right, you can make use of this formula, you can approximate, otherwise this Fermi function will, like at a very high temperature, this will start deviating from this because of the thermal effect. So that is why this formula we are writing here at the low temperature limit. Low temperature for E greater than EV and EF minus E, right? So now it has to be inside the valence band. Okay, I hope you understand why we are doing this thing, not E minus E, because that is for the conduction band. So my energy cannot go beyond that. So now we can write 1 minus Fe, the probability distribution for the whole, which is not only Fe, it's 1 minus Fe, is approximated to okay. So hence the whole density in valence band will be simple, right? So it's basically now we cannot start from EV to infinity. So that basically covers the conduction band and the forbidden region. So that is not applicable. So the limit will be EV only, the upper limit of the integration, but we have to start from minus infinity. Okay. I think this is understandable. Now again, if we do all this substitution like EV minus E by K equals to X, finally we'll get something. I'll just write the final expression, won't waste the time, because that integration, all this intermediate step doesn't make any sense. All matters is you have to remember all this final expression for your exams. but it's better if you do the intermediate step. That gives you the clarity of what are the assumption we are making here, like the way I told, no, that integration from where to where you have to take what region the your expression is valid, this Fermi Dirac distribution. So that gives you the those clarity why we are using this thing. Otherwise you can just simply remember this expression. In short, basically, if you replace this thing the way we have replaced that term as NC, it will be similarly NV, right, for the valence band, and it will be EV minus EF by KT. Okay. So for so these are for this equation what I just wrote. No. So let's say I'm these are important equations. So I am writing this equation, putting as equation 1. Okay. This is equation 1, which is the whole sorry, the electron concentration in the condensed band, sorry, in the conduction band. And this one is basically, okay, the concentration, equation number 2, concentration in the valence band. Okay, these two equations are generally applicable. These are important. You have to understand whether we are talking about the intrinsic or the extrinsic semiconductor, so are applicable. Let me just quickly check this thing. This is in V. Okay, e to the power EV minus EF by KT. Fine. Good. Applicable to both intrinsic and extrinsic semiconductor conductors. Okay. So for intrinsic semiconductor, you know, this concentration should be same. Therefore, if you further solve this, we get something which is very important. This expression I'm writing here for intrinsic, again keep this thing in mind. Sorry, the expression of the Fermi energy. EC, EV. You guys can do this thing by yourself also. ln of NV by NC. This is the characteristic density in the valence and the conduction band, which I already mentioned. Okay, so this already you guys know. I told you what is the effective mass of the hole and effective mass of the electron. Okay, now let's say there are certain assumption. Let's see what we get by doing this. If we assume that your effective mass of hole and effective mass of electrons are equal, then the Fermi energy of the intrinsic semiconductor, okay, lies actually at the middle of the Fermi energy gap, right? So you guys can in the question generally it will be asked, okay, okay, so in the question generally in some cases in the initial condition of the, they will mention ki, okay, this is the condition, my effective mass of the hole in the valence band and effective mass of electron in conduction band is same, then what will be the Fermi energy level where we can expect it to lie in the energy configuration of a semiconductor, right? Intrinsic semiconductor. If this is my EC and this is my EV, you will find it will lie exactly in between of in the Fermiton region, because log of 1 is always 0, right? So that is why you get something like this. Okay. So now, in general, basically this is the one of the assumption, one of the scenario that we can think about. But in general, you'll most of the cases solid, you'll find that effective mass of the electron is slightly lesser, and your Fermi energy, Fermi level is raised slightly with the temperature. Slightly with the temperature. Okay. So now one can calculate the intrinsic carrier concentration, which is n equals to p will define, and which way I'm writing as Ni. Okay. Let's say this is Ni. So now we substitute that equation, that Fermi energy wala. So this I'm defining as equation number 3. 1, 2 already we have mentioned. This is 3. Okay. So now we get the intrinsic density. Let me rather write in red color. This is an important expression for intrinsic semiconductor. You guys have to remember all this thing. And this already I have told what are the values of NC and NV. Okay, I hope you guys already. So if you further simplify, you will get something. If we substitute all the values of the NC, NV and all, you will get something like this. Again, we'll keep on this effective mass will keep on coming into the picture unless it is specified what is the effective electronic or hole mass, and this is your basically gap, the band gap. Okay, if you solve this thing you will exactly get this. EC minus EV, which represents me the band gap. All these things will be provided when you will be asked the questions. Okay, now there is something called like mass action law, which is very important in this context of semiconductor, that I will discuss now. I don't know whether it was discussed in the earlier classes of what sir taken, or anyway, just quickly. So this particular equation number 1 and the like equation 2, which is for the electron intrinsic carrier density for the, yeah, this one applicable to both extrinsic and intrinsic semiconductor. Okay, so the product of the free electrons, what will happen? So let's say under thermal equilibrium. So this is a very important law actually in semiconductor. So if you are in a under thermal equilibrium, the product, let's say we are talking about an extrinsic semiconductor, then this your n equals to p equals to ni doesn't hold, right? The extrinsic cases it could be slightly differ, like np cannot be equal. So we are talking about that thing. But even if it is so, in that case it is defined by a law which is called mass action law. So the which tells us that the product of the free electrons and holes concentration under thermal equilibrium is obtained, can be obtained from the equation like this. So this is a very important one. You have to, this I am defining as a equation number 4. Okay. When you are asked to find out the electronic concentration or hole concentration in the extrinsic semiconductor, but this Ni is actually the concentration for the intrinsic semiconductor. Okay. When it is not doped with something else. And N or P are modified accordingly for, as these are extrinsic semiconductor. I hope you understand this. So this is something is called next. I'm thinking to, yeah, there is some other important stuff also. I will tell you right now. Let me check. Maybe I can discuss some of the problem. So yeah, so I will now discuss the electrical conduction. The electrical, basically your, what will be the conductivity. So this formula you have to remember. 1 second. The total drift current density. This is also another important concept, which is the drift current. Because whenever you try to understand the property of semiconductor, you have to do some electrical transport. So you measure electrical current or voltage, right? In terms of that, you basically define what is the conductivity of some. There will be some parameters called say mobility or charge density that you can define from the current density. Okay, so the total it has both the types of charge carrier. So total current density, drift current density, basically JD. J equals to, from the Ohm's law only. Okay, J equals to sigma E. Okay, and electron and hole mobility are not the same. So that is why you have to slightly be little careful for the electron and hole thing. Okay, these are slightly different. Okay, this formula is very important. This you can consider as a conductivity also. Then we'll see some of the problems actually. That is already it's 4:15. So yeah. So in an intrinsic semiconductor, I already told you this is the expression. I think this I already wrote somewhere back. 2 pi kt by h square 3 by 2. You have to remember this one all the time. 3 by 4, and this is Eg by 2 kt. Okay. Now the drift current density. Sorry. If you have any question, you can ask me in between. Yeah, there is a lot of equation that I'm writing now, but this is important actually. So the drift current density under applied field E right, but for intrinsic semiconductor N equals to P equals to Ni. So JT equals to Ni UN mu P equals to E. That is something we are now defining as a, I was telling you, this is something as an intrinsic property of the material. You guys were familiar in lab also, like whenever you are asked to calculate this thing, you pass a current and measure the voltage just from the standard Ohm's law. You can easily calculate what will be the electrical conductivity of that particular material, whether it could be metal, whether it could be semiconductor, right? But it has a certain conductivity, which is something depending on the 2D, it will have a 3D, it can have some scale dependence, like of the what is the width of the sample or length of the sample. But generally, this is something which is intrinsic, right? So sigma, this you can note it down. This is the electrical conductivity. Okay. Okay. So generally with increase, like if we increase the temperature, the carrier mobility is generally decrease, right? Because due to the increase in the frequency of the